So I kind of prepared a talk that's intermediate between for a more general audience and more specialized. So let's see where we get to. So taking non-relativistic quantum mechanics for a change, seems to us there's enough mysteries there to occupy a long time thinking about it. I'm going to think about two mysteries. One is the issue of non-locality, which we can think about from a couple of perspectives. One is, for example, how can a particle be at two places at the same time when it's represented by something like a wave function like that? And the issue of indeterminacy, or as Einstein would say, well, from Einstein's perspective, God does not play dice. And when I say non-locality, I want to distinguish between two types of non-locality. The traditional one, EPR, what we refer to as kinematic non-locality, and I'll just give you, just for the non-specialists in the audience, as kind of a quick perspective on it. Suppose you've got source of two particles, you send those off to faraway places, you got Alice and you got Bob, and you do measurements on them. Suppose this is your measuring device like this, and now you simply ask the question, you find that every time this goes green, this measuring device also goes green, and every time this goes red, this measuring device also goes red. And you might say, well, how would you arrange that? Well, it's trivial. You just put little sticky notes on the particles, and you say, well, it's green when it started, and this one was green when it started. And similarly, you put a little sticky note and say it's red when that started. So it gets a little more subtle when you add an extra part to your measuring device, and now you say that Alice can freely choose in the future whether to measure the particle in the x direction or the y direction. And so it's an experimental fact that if Alice chooses to measure x and Bob chooses to measure x, then with equal probability, that's what this means right here, half the time they'll see green, green, and the other they'll see red, red. And these are the other permutations. If Alice chooses x and Bob chooses y, and it'll also be green, green sometimes and red, red sometimes, and same for y and x. It's also an experimental fact that if they both were to choose the measuring device in the y direction, then they'll see with equal probability Alice will see green and Bob will see red. So if you try to do this with a sticky note, here's what you see the contradiction. Suppose Alice, suppose this particle randomly, is going to be green, and then you have to follow this right here, and you see that you have to make an assignment of green to Bob's particle, but then you follow this other assignment right here, you see that, well, if Bob's particle is green, then according to this, right, Alice's particle also has to be green. And then you follow this one, and you say, well, also the local instruction when they were first created, also has to be green. And there you see the contradiction, sometimes referred to as the Bell's inequality, so on and so forth. So here you see that the instruction that was given to them when they were created is that y should be green, green, which contradicts with the experimental fact. So that's just the basic, this is well-known, kind of a simplified version of the kinematic aspect of non-locality. So I'm going to talk about that a little bit and give you a very, very different kind of non-locality, what we call dynamical non-locality, which will have a lot of implications with respect to the nature of time. First, I'm going to tell you a little bit about some of the work that we've been doing concerning an issue called time symmetry in quantum mechanics. And so this really starts from the perspective of the basic indeterminacy in quantum mechanics, what Einstein called playing dice. And so, just to put it in a simplified version, suppose you have two identical atoms. Here's the first atom. It decays in 1 minute. Emits a photon, decays to another state in a minute. And here you have an exactly 100% identical atom, but it decays after 1 hour. And so the point is that there was absolutely no difference between these two atoms in the beginning. They were in exactly the same state, but they behaved completely differently later on. And so Yakir, Aharonov used this to argue that this is one of the fundamental differences between classical and quantum mechanics, is that in classical mechanics, even if we know everything that can be known about the initial state of the system, which we can know quite precisely, for example, its position, its momentum, and suppose we know all the interactions that the system goes through, we can, in principle, predict exactly what the position and momentum will be at some later time. But in quantum mechanics, it's possible to set these boundary conditions independently. So if you know everything that can be known, this cat psi, about the system, and you know all the interactions that the system will go through, in fact, you do not know what the final state will be in general, and you only know with certain probabilities. So the argument that Yakir has used is that you can set boundary conditions independently in quantum mechanics. So the standard way of thinking about quantum theory gives you just this one state description, one state vector, which flows in the usual direction of time that, that we human beings experience, and it's given by this expression. And so what Yakir and his group did is they created a reformulation of the standard picture of quantum mechanics. And I'm going to describe to you that a little bit right now. And that picture was really motivated by asking the question, what can we say about the system during the intermediate time between doing the usual thing, a preparation at time t1, and doing something later at time, a post-preparation at time t2. And so now we're going to measure some observable A with your measuring device, and suppose we know all the interactions that are going on very precisely. What are the probabilities for different properties of the system? And so this is one reaction people sometimes have. It's already hard enough to do prediction. Now you want me to do a prediction and a retrodiction. But that's exactly what the basic idea was behind it. So this is famously become known as the ABL paper. And here's the expression. This is well accepted, not controversial at all. This is expression for the probability of some property of some eigenvalue, A sub j, for measuring this observable A at this intermediate time t, given that at time t1, you prepare the system in state psi, and at time t2, you're going to find it in some state phi. And so it's just given by this simple probability. And to show you the relevant things I want to focus on in there, there's this expression, right, which just takes your psi, and this is a time evolution, evolves it from your time t1 later on to time t. And there's this other piece up here which takes the intermediate result A sub j of this ideal measurement of some observable A and evolves it in time from t, intermediate time t, to later time t2. Okay. And so what Yakir and collaborators did is they noticed a basic symmetry here, which is ubiquitous, of course, throughout all of quantum mechanics. And that is the following, that instead of applying this time evolution operator to this intermediate state A sub j, you can apply it to the final boundary condition like this. So here we have the usual one vector way of thinking about quantum mechanics, where you evolve your prepared state forward in time. And then here you have this second different way of thinking about it, where you actually take your post-preparation, your post-selection, and evolve it backwards in time. So this is 100% identical to standard quantum mechanics. It uses just this basic symmetry, which is ubiquitous. Anytime you see a dagger, you can do this sort of a thing. And it led to this time-symmetric or two-vector reformulation of quantum mechanics. And so the basic idea here is, instead of having just a single vector that you evolve forward in time, you have two wave functions, the pre-selected and the second one, the post-selected, which one could interpret as evolving backwards in time. And so the basic object in this reformulation of the theory is this right here. This is not a scalar product. These are two vectors in which we're going to now do interesting things during the intermediate time. And so this showed that the issue of collapse, up to this point, there was a kind of assumption that collapse, even though, if you believe in collapse or not, well, if you believe in collapse, people thought that in and of itself meant that there was a time asymmetry at the microscopic level. But they argued that, well, it is not necessarily that way, that it looks like we kind of snuck in part of our human bias, the way we do predictions rather than retrodictions. So again, just a little review. What ABL showed is that if you do ideal measurements, strong measurements with your measuring device, the ABL formula gives you different probabilities for different eigenvalues. But the key thing I want to emphasize right now is that these are strong measurements. This is like taking a sledgehammer and hitting your wave function, if you believe in wave functions, and then you see these possible outcomes. So you might ask, I'm dealing with reformulation of the standard picture of quantum mechanics, right? In other words, this is not disproving the standard single vector picture of quantum mechanics where you just have states evolving forwards in time. So you may ask, well, why am I doing this? And this is sort of a metric or a signature that, as a group, we try to apply to all such inquiries like this. And so we say that in order for a reformulation to be interesting and useful, it should meet several criteria. One, of course, is that the reformulation should be consistent with standard quantum mechanics, right? There's been a lot of experiments done on it. And that I've just proven to you. There's a kind of an interesting quote from Feynman. Inventing a new theory requires imagination as a terrible straitjacket. Namely, you have to be consistent with all the experiments that have already been done. And so this, I've just proven this to you, that you can use this basic symmetry anytime you see a dagger or a complex conjugate. So I've proven that to you. More importantly, to be useful and interesting, the new reformulation should show you things that you never would have seen from the old perspective. And that's one of the most important things I'm going to focus on, particularly this notion of the weak value of an observable. Thirdly, it should lead to some simplifications and calculations, like the Feynman picture was very useful for doing other calculations. It should stimulate discoveries in other fields of physics, for example, and so on and so forth. And I'll give you a couple examples of this. And finally, the Holy Grail, it should suggest generalizations of quantum mechanics. Should it ever be necessary to actually replace quantum mechanics with another theory, if we find that it breaks down at some point, then the generalization suggested by this picture could give you a very different conceptual framework from which to make predictions. So I want to emphasize something, that everything I'm going to talk to you about up to here, these first three, this is entirely consistent with the standard picture of quantum mechanics. This, although you may have ever seen these, nobody ever saw or suggested these new effects, but there's no, what's the word? From one sense, there's no surprise. I mean, we're surprised, but it's consistent with the standard picture of quantum mechanics. I'll give you a couple of examples of generalizations, and of course, those haven't been proven yet, right? Those require experiments to show that quantum mechanics is not correct. But up to this point, it's part of quantum mechanics. So first, let me focus on this notion of a weak value. We recently had an article in Physics Today. If you want to have copies of it that I can hand out. And you should also see all these reply letters, like in May, and some more to come, another whole round of, it generated a lot of interest, so another whole round of people replying to this. And the basic new insight, one of the main new insights that this reformulation taught us, was this notion of the weak measurement and the weak value of an observable. So again, we start with this kind of situation where we pre-select or prepare the system in some state psi. We're going to measure some observable A, and later on in time, we're going to post-select on some state phi. And then we simply connect to a measuring device, just like we did before when we did ideal measurements or strong measurements, and we just simply weaken the interaction coupling. It's the same kind of structure that was used before, just weakened. And lo and behold, what you see is that the measuring device actually shifts by something which is not an eigenvalue, like ABL showed, but by something called the weak value of an observable. And so, again, the basic scheme here is, instead of hitting it with a sledgehammer, you're going to interact very gently with the system. And let me also emphasize that this applies not only for measurement theory, but for any interaction. And what is the weak value? This is something that was predicted by Yakir Aronov and David Albert in the audience and Lev Weidman. And the weak value of an observable A is given by this quantity right here. And this quantity indeed has very strange properties. I mean, I'll give you one example, which I'll try to work out, in which you'll see, if the pre-selection and the post-selection, the psi and the phi are almost orthogonal, then this thing blows up. It can become very large. It can also be imaginary. So we can give a meaning to the notion of imaginary value, and people have instantly done many experiments like this. So let me give you an example of spin. So suppose you measure your spin electron. Initially, you see in the z direction it's plus a half, and you see later on at time t2, you measure it in the x direction, you see that's also plus a half. And now we're going to make predictions using ABL now about what possible outcomes you might get in the intermediate time. So suppose if at this intermediate time t, we measure in the z direction. Well, ABL, and this is trivial, of course, you see that because you pre-selected in the z direction plus half, in the intermediate time, you must get plus a half for z. Suppose instead that we were to measure in the x direction, and here, this is a little less trivial, but actually still quite trivial. If we're using an ensemble, we are later on in time basically throwing out all the results in which x is equals minus a half. So if we were to ask for that ensemble, what the result of an x measurement would be, then of course it has to be by definition plus a half. So it's a little bit surprising that at this intermediate time, this particle has well-defined values of two non-commuting spin components, sz and sx. You shouldn't be able to do that. But the answer to this is that these were counterfactual in a sense. ABL said with certainty if I measured z, I would get plus a half. It said if I didn't measure z, instead I measured x, then I would certainly get plus a half. So I really haven't done both together. So you might try to put this in the perspective of what would it mean to measure both together. And one way of thinking about this is to measure the spin in the 45-degree direction. So the question is there a sense in which I can take this result of ABL plus a half, plug that in here, and take this post-select result, ABL says this was certainly plus a half, plug that in here, plus a half, and it gets cut off here, sorry. Would I get half plus a half over square root of 2, right, which is too big, right? It's square root of 2 times too big for a spin observable. Spin observable is plus or minus a half, right? This is square root of 2 over 2. So that's outside the eigenvalue spectrum. It's not permissible. You shouldn't be able to do that. So throw it away. No good. But they didn't end there. They became curious. Well, why is it? I mean, these two are certainly true given by ABL. Why is it the case that we couldn't plug these two results into these two observables? And this is sort of the intuition which led to the notion of weak measurements. They found that it depends on the order that you measure these observables. So for example, if you were to first measure in the z direction, then of course, because you pre-selected in the z direction, you of course would see plus a half. If you later then measured in the x direction, because of course you later saw it as plus a half, you would certainly get plus a half then. But suppose you did it the other way around. Suppose you did it, first you did Sx, then you would get plus or minus a half, right? Because it's your post-selection later on. It can't, in some sense, the post-selection can't get through this second measurement, which is of z, which is also plus or minus a half. So reversing the order actually destroys that uncertainty. But the main point is that it was a question of disturbance. Because we were doing ideal measurements, we were hitting it with a sledgehammer. That is the reason, so the intuition went, that we could not see both those results at the same time. So that was what led to the big breakthrough by Aharonov, Albert, and Weidman, that if you do a very gentle interaction, then you don't have this argument that you're actually disturbing both of those boundary conditions. And so in fact, you can plug in the pre-selection and the post-selection for these two observables, and you see this impossible result, which again is square root square root of 2 times bigger than what is possible. And these have been seen in experiments, and it could be arbitrarily large. It could be 100 or 1,000 or so on and so forth. I would just, don't have a lot of time, but we use this, we apply this to many interesting and strange situations, like the Hardy paradox, and several experiments were done to see some unusual properties like negative pair of particles. Another just curious thing I proposed in my PhD thesis, this experiment hasn't been done, but I'm sure it will come out. Everybody knows the Cheshire Cat story in Alice in Wonderland. You can have a situation where you have a cat in one box, but it's smile in the other box. Well, you can do this in terms of pre- and post-selection weak measurements. For example, the analogy in physics would be, suppose you had one particle. You could arrange a situation by pre-selecting and post-selecting it, where you would always see the particle in the right box, but all the properties of the particle, like its magnetic field, so on and so forth, would be in the left box, but you would never see the particle in the left box. So that's just another example of some of the strange kind of things you can see. Let me give you another example. It's a situation involving the famous issue of contextuality. This is the Merman pairs magic square. And it turns out you can use pre- and post-selection and weak measurements, weak values, to have a new kind of proof of the contextuality of quantum mechanics. And something that can be, the contextuality can be tested directly, experimentally. And furthermore, you can argue that there are new kinds of restrictions on the possibility of hidden variables if you want to, if you believe in hidden variables. Now I want to tell you why this is not, there's no problem with causality in this kind of picture. And it's very, very profound. This is a situation here where this is a more realistic situation, because with weak measurements you have to either use an ensemble, large number of particles, and then later on when you do your post-selection throw away a bunch of your ensemble, or you use something with large quantum numbers, like effectively like a ferromagnet or a large spin system. So here we have a situation where we pre-select in the 45-degree direction with an SZ is n over 2, and Sx later on is n over 2. And what this represents here is these green lines are just the ABL probabilities for getting different spin results. The blue is the measuring device when you simply weaken the measurement interaction. That's what you see in the blue. And what the red means is after you actually do a post-selection, you see way out here hidden in the tail this impossible result, square root of 2 n over 2. That's the weak value for a spin in the 45-degree direction. But part of the point I want to make here is you might say that, well, gee, if I do this experiment in the present time, and then I'm going to do the post-selection, 5 years from now, and if I see this result, square root of 2 n over 2, haven't I just violated causality? Haven't I now determined that in the future, when I measure the spin in the x direction, I'm going to see n over 2? And then use that to tell you what the stock market's going to do or something like that. And the answer is, of course, no. You see that the very condition that allows you to see these weak values, namely doing a weak measurement, you see that this condition requires a lot of noise in your measuring device, a lot of scatter. So this is not even drawn to scale. But the point is that the probability of seeing this impossible result purely as a mistake, as an error of your measuring device, is greater than the probability of actually seeing it as a property of the particle, if you would like to go down that road. So let me also just very quickly, I'll do this very quickly. Why is it that it hasn't been seen before? I mean, people have certainly done weak interactions. And everybody knew before this that what you would see is the expectation value of an observable. And let me just give you this sum rule. You can decompose any expectation value into a probability of starting with your pre-selection, ending with a post-selection, times its weak values. Any distribution like this can always be broken down into sub-distributions that are centered around the weak value. Here's another distribution that was one. These are weak values that are more or less close to the eigenvalue spectrum. Here's one where you have one weak value that's well outside the eigenvalue spectrum. And you can see here that the probability of getting those stranger and stranger weak values decreases as they become more and more strange. And this is just a kind of a cartoon as to the difference between doing ideal or strong measurement. You see this is the wave function of your measuring device. That's the spread in it. What you mean by doing a good measurement is simply that you can distinguish the final state from the initial state. And sure enough, no surprise, those are always centered around some eigenvalue. A weak measurement means that the final state of your measuring device is mostly overlapping with your initial state. And so this means that you can always constructively interfere the tails of your measuring device so you can get the wave function set around this impossible result. And this is really how you would, since I told you this is a reformulation, this is how you would understand it from the single vector picture. But it was very interesting because this led to another breakthrough. Remember I told you the third category is that should lead to something, new discoveries in other fields. It led to a new kind of mathematics called super Fourier or super oscillation. It's become a very big area of research. And to give you one example of this, you can arrange a situation where even though you're always getting kicked to the right, you end up with a superposition getting kicked to the left. And so again, this led to actually very practical things called super oscillations. So I've shown you it brought about something new. And I'll give you one or two examples of how it led to some other discoveries in other fields. With the AAV effect, for a spin half particle, for example, you can see spin 100. That was actually the title of one of their original papers, or spin 1,000 or something like that. And so it was suggested that this could be used as a novel form of amplification. And so I had some interactions with my classmate from MIT, Paul Kwiat, and they did this beautiful experiment. They were actually to see a physical effect called the spin Hall effect of light. People thought you would never be able to see it. It was too far lost in the noise. And they used this method to actually be able to amplify it and see it. And people now argue that this is actually the optimal method to amplify signals whenever you have an interferometer. Here's an example where the Rochester group, effectively, this is not the experiment they did, but effectively what they did is suppose you were over here in Seattle, you shined a laser light to New York. They were able to detect shifts of 1 micron, or 1/100th the width of a human hair. And again, there are proofs that this is now optimal. So people are now applying this to all kinds of practical situations, even situations with classical coherent beams like radar and so on and so forth. And I just want to make one note that originally all these foundational questions were virtually unfundable. But when you here's an example of something that became very, very useful, and now it's the governments of the world become very interested because it's such a practical thing. I will quickly give you an example of yet another way of thinking about time. Is this business called multiple time states and multiple time measurements. Basically, the upshot is able to give a new description in which we can unite both the kinematic and the dynamical descriptions of physics, which is a big, outstanding problem. And one of the nice features of this is it allows you to have a covariant description at the level of the amplitudes, which is something that you couldn't do before, right? It was covariant. Quantum mechanics was covariant at the level of probabilities, but not at the level of the amplitudes. But this basic structure, here's an example of a system, and your measuring device is just given by combinations of bras and kets. Here's looking at the resultant of doing a measurement. This object is itself a covariant object. All right, let me give you one other surprising thing. We all know about the basic physics of the separation of different scales. I teach my undergraduates situations like this where here's this white dot is the classical trajectory, and well, here's the wave function, but the energy is sufficiently high that there's not much spread over it. Here's an example where the energy is sufficiently low, for example, that the product of the energy time uncertainty relation is sufficiently big that it doesn't really get centered around that very much. Well, it was always thought that the relationship between the micro and the macro, the correspondence principle, was fairly benign, that the kind of picture of underlying physical processes were very close. So we've come up with situations where it looks like there's a new kind of a whole new perspective on the correspondence principle, which will unquestionably have well, very big implications. Without getting into the details, here's the situation. We have an interferometer. We're using a classical beam of light, a macroscopic beam of light. And this mirror here is movable. Sometimes you see some of the photons are detected here and sometimes here. And what we're able to show is that the underlying processes couldn't be more different. Classical geometric optics says what happens is this mirror moves in this way. Classical geometric optics says that it was because of the photons that are detected here and because of these angles that the mirror gets pushed this way, whereas quantum mechanics says that it had nothing to do with these photons that are detected here. The mirror moved inside entirely because of the photons that were detected there. So you have a complete, even though, of course, the theories agree, right? It's been proven in this classical limit. The underlying picture of physical processes couldn't be more different. Okay, so just some other examples of the third criterion discoveries in another field, and it led to a lot of derivative work. And I might just mention this business of quantum random walk came out of it also. It's one of the most useful tools in the whole business of quantum information. So I've shown you that. And lastly, well, I only have a couple minutes left, so I think I'm going to skip over the generalizations because they haven't been proven. Here's one generalization which you could think that there actually is a future boundary condition on the universe. This is the idea Akira has. It's a very elegant solution to the measurement problem. This is work that we're also doing in collaboration with Paul Davies. And you can start asking very interesting questions about nature of time. There's another kind of generalization which gives you a very different way of thinking about time from the perspective of Heraclides. You ever bathe twice in the same river? I'm going to skip over that. Basically, it literally is a way of, what we're able to prove is if you want to have a picture in which every moment of time is literally a new universe, you have to have this sort of a structure. You have to have these two-vector pictures because it has to be, in order to be consistent with these new states of matter that we call multiple time states, the only way of doing it is with this two-vector picture. Okay. Oh, and I love, David called this block universe on steroids at the conference a while back. My final point is the issue of a new kind of non-locality called dynamical non-locality. Of course, you all know classical physics, the equations of motion are all local. You want to look at the force here, you can only look at the local gradient of the potential in that region. And, Yakir developed a whole other way of thinking about the locality and non-locality in terms of the equation of motion, using the first example of which was the Aharonov-Bohm effect. So it's very different from this kinematic kind of non-locality. This is just a kind of a simulation of the AB effect. You have a magnetic field inside this shielded region. Here there's no magnetic field, and here there is a magnetic field. You see this difference. Even though the particle never went inside, nevertheless the interference fringe is shifted. That's the basic Aharonov-Bohm effect. And so we became interested in applying this to situations like the famous double slit experiment, which you could say, well, if a particle is what we really always see a particle as a thing, like a little billiard ball. How is it that when if the particle is going through this slit, how is it that when you open and close this slit, it nevertheless changes the interference pattern later? And Feynman said that this is the central mystery of quantum mechanics, and nobody knows how it can be like that, and so on and so forth. And you can see, and again, this is part of quantum mechanics. This is not changing quantum mechanics. This is part of the structure of the standard picture of quantum mechanics. You see that there are observables, like this simple example, the translation operator. And if you look at the Heisenberg equation of motion for such observables, you see that they are explicitly non-local. So it looks at the potential here and the potential some distance d away, and it gives you the change of that kind of observable. So there's no correspondence to this in classical mechanics. Of course, you always have to have a local gradient to your field there, but in this situation you have non-local equations of motion. And we applied this to the double slit situation. Incidentally, the original paper that described this was a paper by Aharonov and Peterson and Pendleton. And they also proved that you could never violate causality with this. The thing that's actually exchanged non-locally, something called a modular variable, incredibly, whenever you get to a situation where it looks like you could violate causality, the thing that's exchanged non-locally becomes maximally uncertain. So we became interested in the question is, well, if you arrange a situation you couldn't violate causality for other reasons, like with pre and post selection, would it be possible to observe this new kind of non-locality? And this is just the experiment that we propose. And sure enough, the experiment has been done successfully and has seen this dynamical non-locality. And I'll just, my last slide, I'll mention, there's a, if we really want to understand, get a deeper understanding of the nature of time, we have to think about the basic axioms of quantum mechanics. For example, why is there uncertainty? Why does God play dice? The usual answer is, well, there's no reason. It's just nature is capricious. It's the way of thinking about the axioms goes something like this. We have the uncertainty, for example, which is at this level, and we see that it's consistent, or as Abner Shimoni beautifully uses the phrase, peaceful coexistence between non-locality and relativity or no signaling. The uncertainty seemed to allow those things to live together. But Kira found this to be not particularly intuitive. He says it's like trying to derive special relativity from the wrong axioms. I mean, you can look at all the strange effects of special relativity. If you try to get intuitive understanding from that, you're not going to. But if you use the basic two axioms of special relativity, then all of the rest of it becomes relatively easy to understand. So it's kind of like a joke by Woody Allen. This guy goes to a psychiatrist and says, "Doctor, my brother's crazy. He thinks he's a chicken." And the doctor says, "Well, why don't you turn him in?" The guy says, "I would, but I need the eggs." So it's like the situation in quantum mechanics. It's crazy, but we need the eggs, so we go along with it. So we've not adopted that, and we've tried to take a very different approach to the axioms and say, suppose non-locality and relativity, non-signaling are at the level of axioms. Can we derive the uncertainty from that? And that's been an outstanding research program. So my conclusions, main thing is this time-symmetric quantum mechanics is consistent with quantum mechanics. It brought out new features like the weak values, kind of slogan, this saying by Maslov, if your only tool is a hammer, everything looks like it's a nail. So part of the theme of Aharonov's group is to invent new kinds of measurements and see what comes out of it. And the kind of a theme of that is to grasp the world by grasping it more gently. And it led to all these other results also. I strongly recommend this book, Quantum Paradoxes by Yakir and Danny Rorlick. And final thought. Last time I was here was at this climate change conference in Copenhagen, which all the world leaders came to. And probably it was not it was in December. It was an experience I will never forget in my life because basically the protesters completely shut down the city. It was an extraordinary experience. And people have criticized the world leaders, including Obama, for not really getting too much out of that. Recently, as you may know, Yakir won the National Medal of Science, and I think that Obama gave it to him for actually these two discoveries I just discussed today, and I think that's the AB effect and weak measurements, and I think he got that right. So thank you.